We're going to continue with calculating moments of inertia. And so this is the slide, the presentation we had last week. I did make one addition, and that is I added this table of moments of inertia so we can come back and check to see if we're doing our work right. Mostly that was necessary as I was preparing and doing my practice calculations and making calculus errors. So the calculation that we ended with last class period was calculating the moment of inertia of a uniform plate about its axis through the center. When we talk about moments of inertia, remember, moment of inertia depends on the axis you're rotating about. And so this is called this moment of inertia about the z-axis. It's IZZ because it's a tensor, right? It has two subscripts, one for alpha and one for torque if you're going to be doing the torque equals I alpha equation. Okay. So it's the one that relates torque in the z direction to angular acceleration in the z direction. So that's why I have the IZZ there. If we go to where we ended our work last class period, we ended at this equation. And we were just out of time, so we had to stop there. So I'm going to actually pick up and just do the last line I just said, and from here it's just simplification. So what I'm going to do is factor out sigma LW over 12. And then what we want our moment of inertia to be in terms of is the mass, not sigma. What was sigma?
I love those notes elsewhere because
it's okay.
Space.
It's okay. I asked the question because it's important that we remember what we're working with. And it's been a week. So sigma was the areal density. That was the mass per unit area.
Okay.
So since sigma equals mass over area, and of course, for a rectangle, area is length times width, then I can put that in here, and I have IZZ is equal to, for sigma, I'm putting mass over length times width, and then just keeping on with the length times width over 12 times length squared plus width squared. Width, not weight.
Width, yeah.
So there's the end result. You see, we were very close. I just, it took a minute and we didn't have that minute. So now if we go back and check our table, we have a slab about the perpendicular axis through the center, mass times a squared plus b squared, length squared plus width squared over 12. Yay, we did it right. Yeah.
Not the ones you did wrong.
All right. Moment of inertia of a uniform disk. What's the axis you would expect me to rotate it about?
The center.
Okay, the one that's labeled as
G.
G is a point.
Yeah.
Z is the axis.
Okay, yeah, that axis.
Okay.
But it's going through point G.
It is going through point G, but so are the X and Y axes.
Oh, fair enough.
So that's what notice we have here, IXX equals IYY equals 1/4 MR squared. What does IXX mean based on what I said a moment ago?
The rotational inertia or not inertia. It's
moment of inertia.
Yeah, moment of inertia around the x-axis.
Okay, that's good enough for us, right? Remember, it's a tensor, so there's an x, y, and a y-axis and whatnot. But x-axis is around the x-axis. I-y-y then would be around the y-axis. What about then we have I-z-z and I-z prime z prime.
Well, z is around the z-axis. As for what z prime is, not a clue.
That's about the axis that's labeled there as z prime.
Oh, that one.
Because if you do it about there, it's going to be different. So let's go ahead and calculate. First, we'll calculate IZZ. Why are we going to do IZZ first? Because, you know, I mean, when you're talking about throwing a frisbee or whatnot, that's the axis you spin it around. So, space, final frontier.
This is a strong class.
Questions to ask. Like when you come to the test, if I ask you to calculate the mode of inertia of an object, questions to ask are, what coordinate system should we use? So you answer me. What coordinate system should we use?
What coordinate should we use?
The typical coordinate systems are the Cartesian coordinates, x, y, and z. The cylindrical coordinates, which I use, I have on this picture, are theta and z. Or the spherical coordinates, which once again, I have to say I because some people use rho for radius instead of r for radius. The spherical coordinates, where what I'm used to using is r, theta, and phi. So, which coordinate system would you use to calculate the moment of inertia of a cylinder or a disk?
Probably the circular ones.
Okay?
Yeah, I guess, because you're spinning it around an axis, and if you kind of like draw a mark on it, the theta is going to change as it moves around or something. So that makes no sense to me.
Okay. What do you think, Randy?
I can't really, I don't know.
Okay. Well, I expected you guys to say the Cartesian because we're most comfortable using the Cartesian coordinate system. Your answer is the easiest one, Dave. Based on its symmetry, it has cylindrical symmetry. It has symmetry about a single axis. And so cylindrical coordinates are going to lend themselves to the easiest calculation because of that symmetry. And as we go on, especially as we get to second semester, this whole symmetry thing is going to be more and more important as we do calculus, things to simplify our lives as much as we can. So I have written out, this figure is on the next couple slides as well, but the two different options where in cylindrical coordinates, you define something by the radius away from the z-axis and the angle from the x-axis and the height above the xy plane. And so you can use just normal trigonometry to get your x, y, and z components in terms of r, theta, and z. In fact, it's pretty simple, right? If you break this up into a triangle, r is the hypotenuse, x is the adjacent side, y is the opposite side. And so you're going to have x is equal to r cosine theta because it's adjacent, y equals r sine theta because it's opposite, and z is just equal to z. So transferring from one set of coordinates to the other is kind of simple. What's not as simple is the dv. So I have dv actually on another slide, so I'm not going to write it down right here. But that's the first thing you have to ask yourself is, what coordinate system am I going to use? Now, I am going to start the problem with Cartesian coordinates to show why that's not the right answer. Then I'm going to go and do the problem in cylindrical coordinates. Okay, so then we have to answer, once we determine what the coordinate system is, what is dv? For Cartesian, what would it have been? I have it on the next one. What would it be? What's dv for Cartesian coordinates?
Are you asking for the change of velocity?
No, d volume. That's a good question, Randy.
Something times area.
Well, you have 3 dimensions of space, and if we make a cube, its volume is length times width times, well, cube. A right rectangular shape, parallelepiped or something like that, I don't know. Right rectangular prism, something like that. It would be the x component times the y component times the z component.
Right.
So in Cartesian coordinates, that's just going to be dx times dy times dz. That's dv is a little tiny infinitesimal piece of volume with lengths dd or dx, dy, and dz on the sides. So that's kind of easy. It's just, I think of it as a cube because my brain goes to cube.
Is that a cylinder?
Well, that would be if I was using Cartesian. Now, this picture here is actually the picture that goes with the cylindrical piece of volume. And so 2 slides from now, I'm going to go over that carefully. What is R perpendicular? If I was using Cartesian coordinates, how would I find? Now, remember, R perpendicular, what does that perpendicular mean?
Perpendicular to where your R is headed. So if it's headed this way, if that makes sense.
That is true, but the R's direction is perpendicular to the axis I'm rotating it about. And so that would be the z-axis for this calculation. So when I say R perpendicular, I mean, what is the R vector that's perpendicular to the z-axis? Now, like what you said, Randy, was true.
I see what you mean about the axis.
Yeah. And so if you're using Cartesian coordinates, it'd be square root of x squared plus y squared. If you're using cylindrical coordinates, it's just R. R perpendicular is R. There's already simplification. And then we have to worry about the limits of integration. What are the limits of my variables? And so let's just go to what it would be for Cartesian coordinates. So in Cartesian coordinates, my R perpendicular is square root of x squared plus y squared. Pythagorean Theorem. And dv is dx, dy, dz. Real simple. But then the limits, and for reasons only God knows, I have this over on the left side repeated on the right side in smaller font. I didn't even notice that until now. So my limits, well, let's just write this out. There's our starting equation every time. IZZ is equal to integral of R perpendicular squared dm. And then we make our substitution that dm is equal to rho dv. In every problem that I am doing in class, rho is constant. Rho may not be constant. I may give you a question on the test where rho is not constant. All that means is your integral is going to have a different integrand because you're multiplying by rho. So it is an increased complication because the integral is harder. But it's not increased complication in concept or anything else. So I just want to make sure I point that out so you don't think, oh, rho is always constant. So dm is equal to rho dv, where rho is the mass over volume, which would be, what's the equation for the volume of a cylinder?
1.5 height.
It's basically the equation for a circle times height.
Right. The area of a circle, which is pi r squared, times the height.
Yeah, no, definitely.
So that's what the density is. And then we already had the R perpendicular written right there. So now I can why do I now have 3 integral signs instead of 1?
Because you're taking the integral 3 times.
Because it's a triple integral. Now, in your calculus class,
Because you've got dx, dy, dz.
yeah. In your calculus class, I know Randy has learned to do triple integrals. You're not yet?
Nope.
A lot of times you can simplify this.
I didn't stay in class, no.
Oh,
That's
really?
what I thought, yeah.
Oh, I thought Randy was in.
No, it's how 2 right now.
Okay.
For this.
Okay. Fair enough. There is a way often to get around doing a triple integral. And that is to say, okay, and this is the way you will look at it first, I think, when you're doing a calculus. If you have something and you want to integrate the volume, you say, okay, I have a shell of this area, and then I integrate that over the radius. And so that's a way to get around it. Cartesian coordinate system is just never going to be good for us here. But I'm going to do everything as triple integrals just because I think it's good to see them in practice and see that you're really not buying yourself a lot by doing the simplification of changing it to a single integral. Although, remember, this one here is going to be really hard and we're going to scrap it. So I have to have my limits, and I'll put dz, dy, dx for the order. So I put those, actually let me Let me color coordinate these. Okay, so by color, I have them separated. And then I have to put what my integrand is. So my integrand is r perpendicular squared. R perpendicular was square root of x squared plus y squared. But since it's perpendicular squared, I get rid of that square root sign. Rho. And then the dv, I already had those there combined were the dv. So that's my entire integral, except for what am I missing from this integral? I'm missing something that is really necessary.
dx or something like that. D respect to something.
I have those. I put them with the integral signs instead of at the end. It's an alternate way of writing it.
Okay.
So I do have those. The reason I put them there is so we know which integral goes with which variable.
Yes.
And then I chose to color code it so I didn't have to. But what I'm missing is limits.
The limits of the integral.
The limits of the integral.
They're not, this is not defined.
Yeah, it's defined because I have a finite object. The object doesn't go on forever, right? And so let's start with the easy one. The z-axis. In our picture, we just have this little thing of very negligible thickness. It doesn't matter. It could be really thick. It's still a cylinder and a flat disk are the same answer. So I'm just going to say it has height h. And so if it has height h, then my integral, my limits for z are going to go from 0 to h. Now dy, what's the extent of the y variable? Once again, looking at the picture, y is going from plus r. And of course, I need to actually make my limit go from minus r to plus r. So that's easy enough.
That's the same for the x, isn't it?
Oh, you wish. If it was the same for the x, this would be easy. But it's not. Let me show you why. Let's say that y is right there. Okay. Here's my y value. X can go from here to here, which is less than r. So how do we find that limit?
So it's going to be based off of y.
It's going to be based off of y. We know the radius here is r. And so if I use the Pythagorean theorem, I'm going to have, of course, x squared plus y squared equals r squared. So solving that for x squared equals r squared minus y squared. And so my limit for x is going from minus square root of r squared plus y squared, or minus y squared, to plus square root of r squared minus y squared.
Did we not take square roots of those?
No, we do. That I was just showing x squared there. And so x is going from minus square root okay, there it is. It's short and concise. What's the difficulty here?
That's going to be to work with.
It's going to be painful to work with because I have that square root stuff in the limit. And so when I do the x integral is trivial. Yeah. X cubed over 3 plus y squared x over 1. But then I substitute in those limits and I have these square roots of r squared minus y squared times 1 times y squared.
Right.
And that integral isn't pleasant. I looked it up on Wolfram Alpha. Wolfram Alpha could do it. I tried to do it on software I have on my computer that does integrals. It couldn't do it. We've learned things, tricks of how to do different types of geometric integrals. Or you can look in the CRC handbook, as we did in my day, to see the table of integrals and figure out how to do it. But it's difficult. And so we're going to stop here because we have another way that's not difficult. Question? You're doubting me on the not difficult part?
No, it's just like, wow, so something that you can
So here we switch to the cylindrical coordinates. Now, if the cylindrical coordinates, my r perpendicular is just r. So r perpendicular is a little simpler. And my dv, sometime in Calc 3 should you take it, I believe you'll get to where you find dv for cylindrical and spherical coordinates, is r theta dz. Now, when you look at that, you're like, that's really weird, because it has a variable here that's not part of a d. But think about this. dv has units. What should the units be for dv? Units of
It's like
length.
X, Y, Z.
Right, it's volume, and volume has units of length cubed. So this needs to have units of length cubed. dr, that's length. dz, that's length. d theta, what's the unit for angle? Degrees is a derived unit. The fundamental unit is radians, which is no unit. So theta is unitless. So we have meter times meter. It has the wrong units unless we have something multiplied that has units in it, units of meters. Now, how we get that is, and I know the picture looks fine until you zoom in, then everything gets all a little fuzzy. But we have a little wedge of volume. So this thing here, if you take the volume of this, that's dV. Okay, so if you take the volume enclosed by, oops, I forgot one line. By all those purple lines, that gives you dV. Now, of course, I'm going to erase all of those because they muddy it up. I just wanted to make sure we understand what we're finding the volume of.
Take the integral of that.
Well, we're taking the integral over dV, and that is the piece of volume dV.
And then the shape gets smaller to get that entire volume.
Right, then we're varying r, theta, and phi to cover the entire volume. So this is not a rectangular figure, right? But if theta is small, it becomes closer and closer to rectangular. And remember, when we're doing d, that d means infinitesimal, on the order of 1 over infinity. So that means our angle is on the order of 1 over infinity. We can treat it as rectangular. Even though my picture is accurate, and thus it doesn't look rectangular at all. But because we're taking this to the limit of very small d theta, we can treat it as a rectangle, and this side here is dr. That's a small change in radius. This is an arc here. Nice, I missed that. That's an arc, and the arc length is equal to the radius times the angle that you subtend, or r d theta. So that's why it has r d theta written there, because that's the length of that arc. And the height is, of course, just dz. So if we're in the limit of very small d theta, what we have are three sides of a rectangle, or a rectangular prism. And so the volume of this is going to be this times this times this. So we just have dV is equal to r d theta was one of them, dr was the next one, and dz was the last one. So those are the three sides, and that's how you get the dV. Now, of course, there are very few students alive who think about this derivation at all after it's first been shown to them. They just learn or memorize, you'll have given on the test, that for cylindrical coordinates, dV is r d theta dr dz. So I'm giving it to you so you can understand where it comes from, so it's not some magic that just popped out of thin air. There is one thing on this picture that might confuse you still. R plus dr d theta, that's bigger than just r d theta.
Yeah, but that arc is bigger.
Yeah.
The what?
That arc is bigger though.
Right, that's what I'm saying. The arc is bigger.
Adding the arc.
Well, the length to the back side of my shape is r plus dr.
Yep.
Right, because dr was the width going out parallel to r. And so that arc length is a little larger. But the thing is, dr d theta is 1 over infinity times 1 over infinity.
So it's infinitesimally small.
So it's negligible compared to r d theta. And so we just drop off that term because it's negligible.
That makes a lot of sense.
So you can see there's a few approximations that it's small enough that we can treat a rectangle and that we can drop off that dr d theta term. So we've got our r perpendicular, we have dv, then we need our limits. And with the cylindrical coordinates, if we have cylindrical symmetry, we've decoupled the limits. That is the limit for y dependent on, or for x dependent on y with Cartesian. That's coupled. Here it doesn't. Our radius goes from 0 to capital R. Our angle goes from 0 to 2 pi because you go around a complete circle. And our z goes from 0 to h. It's going to be an easier integral because of the limits.
Or easier.
So let's do this. So we're going to do IZZ again. Integral r perpendicular squared. Wow, that was pretty beautiful. dm, which is equal to a triple integral now. And once again, I'll color code it. And I'll color code it using 0 to h dz. 0 to 2 pi d theta. 0 to capital R, and then we have rho times r perpendicular squared times r dr. So this r dr, I'm going to do further color coding. So my black is the integrand, the thing I'm going to integrate. And then I have the colors for each of the integrals and limits coded together. Well, what you notice here is that r perpendicular was just r, right? R perpendicular was just r. I couldn't figure out how to put perpendicular. That's why I have the word perpendicular spelled out. And so this is
Makes a lot more intuitive sense.
I think so as well. So there I substitute r perpendicular as just r.
We can do that?
We had to do that.
Oh, we had to.
We have to substitute for r perpendicular, so we had r perpendicular as r.
Oh, okay, so that's just automatically a thing. Okay.
Right, so I mean, when we did the Cartesian, r perpendicular was a more complicated thing, but we still had to make that substitution.
And that Cartesian is equal to r, because if it's a triangle.
In the cylindrical, yes.
Okay. Cool.
So why is this simpler? There is no coupling of any kind. This is, go away. This is all a function of r.
Yeah.
This is all a function of theta. This is all a function of z. So I can do each color separately.
Yeah.
So what's the integral from 0 to h of dz?
H minus 0.
Okay, so we'll just put h.
Yeah.
We're good enough to, it is good that you said minus 0, but we're good enough to know that. What about integral from 0 to 2 pi of d theta?
2 pi minus 0, so 2 pi.
Right. And finally, what's the integral of rho r cubed dr from 0 to r?
Times r to the 4th over 4 times... Yeah, that.
This time I put the limits explicitly.
You can't
just because I didn't want to combine them. But we can see in this case when I put in the lower limit at 0, so it's just going to be rho r to the capital R to the 4th over 4.
Yep.
So put it all together.
So integrals is mean multiplication, just to multiply all integrals after they're solved, essentially.
If they're uncoupled. That's uncoupled means that one integral doesn't depend on another. But when we did the Cartesian, it wasn't that way. That's why we stopped, because they're coupled, because your limit for x depended on y. So you couldn't do the y integral first. You have to do the x integral before you can do the y integral. And the y integral depends on your x outcome. And so that's why we're using these coordinates, because it decouples it, makes it simple. So there we have it. Rho h 2 pi r to the 4th over 4. Now I want it in terms of mass, not in terms of rho. So I've already derived very quickly what rho was. Just recall that rho was equal to the mass divided by the volume, which was pi r squared h. So if I plug that in here,
H is pi and r squared.
okay?
I'm left with 2m r squared over, right? M r squared over 2. And scroll up to the table.
Scroll up to our table, and that's what it says. Yeah, it'll be, I add, no, it's just further up. Yep. I thought I was right on. So that was for a cylinder about its symmetry axis. Bueno. Feeling good? C. All right. So now we're going to do one, and of course we have them right here. Now we're going to check this one. Now I don't have a slide to check it. We're just going to do it. So if we're doing about the XX axis, I'm going to come over here and do it. So I am doing it rotating about this axis. Well, it's a disc, which I have none of here. You got one of everything, but
The
it's.
square thing that your section comes on.
Let's imagine this is cut off at the top. We are now rotating about an axis like this. Now, in this case, the thickness actually matters. We're going to do it in the limit where the thickness doesn't matter. Why does the thickness matter? Because you need to calculate r perpendicular, and you're going to have a certain vertical or a certain aspect, this direction, to go along with it. So we are approximating to the thickness is approaching 0. Because if the thickness is non-zero, it's going to start being different. And it's going to start making our lives harder again. I want to keep these integrals decoupled. So, where do I measure my r perpendicular from?
Wouldn't it be kind of the way you have it drawn kind of into and out of the screen?
Well, I drew it so I could do it this way. So if I'm at this position here, so this is lowercase r, and this is my angle theta, then the perpendicular is perpendicular to the x-axis.
Okay.
So that's my r perpendicular.
Gotcha.
So what is R perpendicular equal to?
Sine theta r.
I made the oscillator work.
Oh, yay. Your circus class. So R perpendicular is R sine theta, right? We have to find that. And then what do we have to find next? By the way, if we wanted to be really anal, we would have had this here squared plus z squared.
Why?
That would be if it has thickness that's not negligible.
Oh.
So that's
We don't have that, so we're not.
yeah, we don't have that because because that's going to couple the z integral with the other two. So dv is equal to same as before, r dr d theta dz. And of course, density is the same as before as well. So we go to our integral. Zero to h dz. My h is negligibly small, but I still have to have that there since I'm doing a dv. And then integral from 0 to 2 pi d theta, integral from 0 to capital R, r dr, and then my integrand, which is r perpendicular squared rho. But r perpendicular is not the same as it was last time, so this is where it changes. So now r perpendicular is r sine theta.
Which is a bit more of a pain.
Now, I'll write this with the straight substitution instead of jumping one step ahead. And so I have r squared sine squared theta because I have to square r sine theta times rho. Now, in terms of color coding, this r is going to go with that, but this sine squared theta is going to go with that. Since they're multiplied, I can move a theta through the integral for r.
Okay, so you can simply move that sine squared theta all the way over to the theta part.
Because it doesn't have anything to do with r.
Cool.
Right? If it had an r that was part of it, if it had like, sine squared of theta times r, no, I could not bring it through. So I can keep this decoupled, and that's why we're doing the approximation of no thickness. Nice color change. And I can't forget the rho, which I think I might have forgotten in the intermediate term up here. I don't know. Okay, I've moved up above actually what I did last time, so we'll find it later. So now we can do these separately. What's the integral from 0 to h of dz?
H.
What's the integral from 0 to 2 pi of sine squared theta?
Something disgusting that I can't recall right off the top of my head. It's not.
Negative cosine, right? Something.
No,
Okay.
I don't think it's that.
No, it's
sine
not that
squared.
simple. And so you know how I do this? I do this graphically. If I graph sine squared theta, what does it look like?
I don't know.
Well, you're about to learn. First of all, sine squared theta never goes negative, right?
Yes.
Because it's squared.
Mm-hmm.
And sine theta has a maximum magnitude of 1, so sine squared theta has a maximum magnitude of 1.
So it just bounces back between 1 and almost 0?
At what value, or what is the value of sine theta at theta equals 0? What's sine of 0?
0.
Okay, so it's going to start here. What about at pi over 2?
Root 2 over 2, is it? No, I don't think so. Yeah.
At pi over 2, it's 1.
Oh,
Sine,
yeah,
sine of
it
9
is.
degrees is 1.
Yeah. And then at pi it's 0, 3 pi over 2 is 1. And then 2 pi is 0.
And of course, it's a sinusoid, so it's actually going like this.
Yeah.
And it's symmetrical. Since it's symmetrical, what's the average?
1/2.
And you know that an integral is the area under the curve. So if I know the average is 1/2 and it goes for a distance of 2 pi, what's the area under either the dashed green line or under the solid red line? Well, it's base times width. Or base times width, base times height.
Yeah.
Base and width would be the same. So the base is 2 pi, the height is 1/2. And so the integral, the area under this, which is either that green hash, which is the way I actually did the calculation, or the red hash, which is the true integral, is 1/2 times 2 pi is just pi. To quote Randy. And then we have the integral of r cubed dr. Well, we already did that.
So capital R to the 4th over 4.
Now, how is that different than what we just did?
From what we did earlier, and the other one, which I don't remember.
From what we did here. The only difference is that had a 2.
Yes.
So without doing any work, I can rely on that to say, well, I know this is going to break down to be half as big as the other one. But we should do the work.
The other one was, yeah,
So I'm doing the full work.
okay, so it's just the R squared over 4.
So looking at canceling, pi's cancel, h's cancel, r squared cancels with 2 of those.
In R.
So now we've done these two. Could you reproduce it?
Yeah.
Good. What if rho was a function of, let's say, rho is density. Let's say it's a function of the radius. How would your solution be different? It would, because rho would not be a constant anymore. I couldn't just slide rho out. If rho is a function of radius, it's got to stay in the radius, so that the orange integral would be more complicated because of whatever that function is. Unless, of course, I did something like said, well, the density is rho 0 over radius squared, which of course means it can't go to 0, so it'd have to be a ring then instead of a complete cylinder. That would make it simple because of low dimensionality. You would also have the mass you'd have to actually calculate, because that equation, density is mass over volume. If that's varying, then you would have to say, well, mass is the integral of density dV. So you would have to also integrate the density over your volume to get the mass.
You're saying density
Density is mass per unit volume. And up to this point, we've been saying if the density is constant, boom. But if the density is not constant, then the mass of the object is not just density times volume, because the density is not a constant value. You can just multiply.
Sure.
So instead, because it's changing, you have to add up the density times this little dV plus density times this little dV, add them all up, which we call integration. And so your total mass is the integral of density dV. So now you would have two integrals, one the integral of density dV, and then one the I integral we've just done. And then you could substitute in the mass in the end to get it in terms of mass. All right. I am not going to do the calculation about the y-axis. Why not?
Because about the y-axis is the same as
Yeah, the symmetry is exactly the same as about the x-axis. I think I'm funny. I'm also not going to do it about the z prime axis. What that would do would be essentially give you a proof of the parallel axis theorem. But what's the point? We've got only 4 minutes left.
Yes.
Well, then we only have time to set up the moment of inertia of a solid. Wow. And in practice, I set up doing an annulus as well. An annulus is a cylinder that has a hollow center. So essentially a ring. If we have a sphere and we want to find the moment of inertia of the sphere about an axis going through its center, notice because of the symmetry, I just say the axis going through its center. Any axis going through its center is the same. What coordinate system should I use?
Would the Cartesian do just fine?
If you like pain, yeah.
Okay.
Because
just looking at the way you've written it, I mean,
You could somehow,
your x, y, and z integrals would all be coupled.
oh, well, never mind.
this is a weird idea, but it looks like it's a cylinder, right? Could you integrate whatever we found out the cylinder to be with all the heights and everything like that?
You could do it as a cylinder with the height varying with radius, but then you're coupling variables again.
Shoot.
But it has spherical symmetry, so we use spherical coordinates. That uncouples it. Right, so there's a reason for these different coordinate systems besides making life hard in calculus class. It makes life easier in physics class.
Well, I guess it's made for physics, so.
That's why it was invented. Let's not forget. Okay, what coordinate system should we use? We should use spherical to match the symmetry.
Were we just working with the spherical coordinates?
We were doing cylindrical.
Cylindrical.
So we're working with 3 different coordinate systems today: Cartesian, cylindrical, and spherical. What is dV? Well, for a little piece of sphere, yeah. Okay, here I have the dV. It's r squared sine theta dr d theta d phi. So it has 2 angles, which is why you have to have 2 things out there with units of distance, which it turns out is r in each case. And the geometry of making the shape is a little harder. Remember I did this side is r d theta and this side is dr and this side is, it's a little harder. But your r perpendicular is going to be r sine theta. Now theta is an azimuth angle. Theta is an angle that's 0 degrees here, and then it goes down to pi. You also, that's altitude angle. That's altitude angle. Probably pretty clear the way I did my arm that it should have altitude. Phi is the azimuth angle. It goes from here all the way around 2 pi. So phi has a limit of 2 pi. Theta has a limit of only pi, 0 to pi. Why the difference? Well, if they were both 0 to 2 pi, I would go from here to here, and from here to here. I'd cover the entire sphere twice.
But if you're only going from here to here,
Then this is covering half the sphere, and then I go all the way around, and I got the
which
whole.
covers all of it.
So, We are just about out of time, so let's just do the work in quick. I don't need to put x, x, y, y, z, z. I any axis. I'll put z, z anyway. Is equal to integral of r perpendicular squared dm, which is equal to integral from 0 to 2 pi d phi, integral 0 to pi d theta, integral 0 to capital R, and then we have our r perpendicular squared, which is r sine theta, y squared rho, and then r squared dr. Now, I didn't color code this because we are out of time, but if you look at this, it's still separable. It's separable, so I can make this equal to integral from 0 to 2 pi d phi. And my d looked a lot like a phi, didn't it?
Yeah.
And then
Integral from 0 to pi of sine squared theta.
oh, I forgot something. Ha! The dv, I forgot that in my practice as well. I got a wrong answer. I'm like, what in the world? dv has sine theta in it. So it's sine cubed theta. And then we have r squared times r squared is r to the fourth. And let us, yeah, let's not forget it. Well, the first integral is easy. The second one, if you substitute that sine squared theta is 1 minus cosine squared theta, and then you do a u substitution that u is cosine theta, so du is minus sine theta d theta, it actually comes out pretty quickly. This is 4/3.
4/3 pi?
No, 4/3.
Oh.
And then the last one, well, we can do that one in our heads. R to the 5th over 5. And so you have rho 4/3 pi r cubed times, so I used up this 4, this 3 of those, the pi. I did not use the 2, I did not use the 5, and I did not use an r squared. This here is the mass, so it's 2/5 m r squared. Obviously, I did this last one really quickly.
Yeah.
Not nearly the explanation because, hey, I spent a lot of time explaining earlier. Cool. Have a great lunch, and I'll see you after lunch.
This lab won't take too long, will it?
No.